Today's podcast is on the rational root theorem. When you want to solve a polynomial equation, it is helpful to have some idea of possible roots. This is where the rational root theorem comes into play. Basically, if you have a constant as the lead coefficient and a constant again as the last term of the polynomial, at least one binomial will have to have factors of these constants. In mathematical terms, a sub 0 has factors q, and a sub n has factors p. The possible rational roots are all the possible combinations of p over q. As an example, we have this problem. We have 6x cubed plus 11x squared minus 3x minus 2. A sub 0 is 6. A sub n is 2. So first I looked for the factors for p, and the factors of 2 were 1 and 2. Then I looked for the factors of q, and the q factors are 1, 2, 3, and 6. At this point, because we don't know the signs, everything is possibly positive or negative, I did every possible combination with 1 as the numerator, and then every possible combination with 2 as the numerator. So I started with 1 over 1, 1 over 2, 1 over 3, 1 over 6. Then I started again with 2. 2 over 1, 2 over 2, 2 over 3, and 2 over 6. If you notice, 2 over 2 reduces to 1, which was our first possible, and 2 over 6 reduced to 1/3, which was our third possible. So my final result is my possibilities are plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, plus or minus 2, and plus or minus 2/3. To determine the actual roots, you could test each possible value using the remainder theorem, and that's what's at the bottom of your note sheet. And this is just all the work shown out. And if you notice, when I did p of 1/2, it did work out to 0. That meant one factor was 2x minus 1, because if you have x minus 1/2 equals 0, and we want our binomials to have only integers involved, I multiplied both sides of the equation by 2 to eliminate my fraction, and ended up with 2x minus 1 equaled 0. The same situation worked when I worked with negative 1/3. I had x plus 1/3 equaled 0, so I multiplied both sides by 3 and got 3x plus 1. You can see from here that the three possible roots from the degree of 3 were, or three factors were, 2x minus 1, 3x plus 1, and x plus 2. The actual roots were 1/2, negative 1/3, and negative 2. Now, a way to lessen the work, we tested an awful lot of possible roots on that one, would be to actually graph the function. So from that example, this is the graph. I graphed it on my calculator and then just kind of sketched it onto my graph. I can see that it looks like I definitely have a root at negative 2. I would check it by substituting in p of negative 2, but these are the ones that I would actually have checked for this one. I would have checked negative 2, negative 1/3, because that's the only value I had between 0 and negative 1, and then I didn't know if the other one was at 1/2 or 2/3, so I checked both of those. It just cuts down on a lot of the extra work. I only had to check 4 possible factors instead of all of them. Now, the integral root theorem says that if all the possible roots are integers, then the rational roots are integers. So we could actually find those with quadratic formula. I started with a different example. I have x cubed plus 6x squared minus 13x minus 6 equals 0. P in this case was 6. Q in this case was 1. So the factors of 6 were 1, 2, 3, and 6. The factors of 1 is just 1. So my possibles were plus or minus 1, 2, 3, and 6. Then I checked the graph. And on the graph, the only one that looked really good was 2. So I evaluated p of 2 and found out that yes, x minus 2 was going to be a factor. 2 2 was a root. To find the remaining factors, however, and the remaining solutions, I did synthetic division to find my depressed polynomial. The synthetic division is shown on your sheet, and you can see that your depressed polynomial is x squared plus 8x plus 3. Now, to finish that, I just did the quadratic formula. So I did x equals negative 8 plus or minus the square root of negative 8 squared minus 4 times 1 times 3 all over 2 times 1. As I worked it out, I ended up with x equaled negative 8 plus or minus the square root of 52 over 2. I simplified the square root of 52 and got x equals negative 8 plus or minus 2 square roots of 13 over 2, and then factored out and divided out the common factor of 2 and ended up with negative 4 plus or minus the square root of 13. So that's 2 roots, and then the third root was 2 that we had previously found. These are just some practice problems for you to do. Go ahead and do them, and then check your work against the podcast. Check your answers. On the first problem, the possible rational roots were plus or minus 2 and plus or minus 1. 1 worked out when I substituted into the polynomial function. My remaining factors were x squared minus 3x minus 2. I knew it didn't factor nicely, so I did check by doing the discriminant. The discriminant was 17, which meant that the square root of 17 is an irrational number, so 1 was my only rational root. On the second problem, my factors for p were 1 and 3. My factors were q for 1 and 2 for q. So my possible rationals were plus or minus 1, plus or minus 1/2, plus or minus 3, and plus or minus 3/2. 1 was a root, so I substituted it into the problem and came up with a depressed polynomial of 2x squared plus 5x minus 6, which I then factored and determined that x could also be 1/2 or negative 3. There are still other old techniques that can help you determine the nature of solutions to a polynomial equation. While most can be easily determined with a calculator, it's still important to understand the theory and the history that goes along with the mathematics. One of these other techniques is Descartes' rule of signs. It can help you determine the number of positive real roots when you look at p of x and the number of negative real roots when you look at p of negative x. It's actually based on the number of times the signs change in p of x or p of negative x. Looking at our example, p of x is 2x to the fourth minus x to the third minus 2x squared plus 5x plus 1. When I substitute in a positive number for x, I have a positive, a negative, a negative, a positive, and a positive. What I'm actually looking for is how many times the sign changes. It changes once from positive to negative. It does not change from negative to negative. It changes once from negative to positive, and it does not change from positive to positive. So the total number of sign changes is 2. That means there are either 2 positive real roots or 0 positive real roots. That's because you could either have 2 positive real roots or you could have had 2 positive imaginary roots. So if it's 2 positive real roots, you have 2 positive reals and 0 positive imaginaries, or you could have had 0 positive reals and 2 positive imaginaries. Remember, imaginaries only go in pairs. Now, when we substituted in negative x, when I did negative x to the fourth power, it became a positive, so my first term was positive. When I did negative x to the third power, it was a negative, so minus a negative became a positive. When I substituted in a negative x for x squared, it became a positive, so a negative times a positive was a negative. 5 times negative x is a negative, and positive 1 was a positive. Again, looking for changes in sign. There is no change between the first two terms. It changes from positive to negative in the next position. No change between negative and negative, and the last possible goes from negative to positive, so it had one change. A total of 2 changes, which meant we could have either had 2 negative real roots and no imaginaries, or we could have had 0 negative real roots and 2 negative imaginary roots. Now let's go ahead and take that problem and actually determine the rational roots. So our P was 1, our Q was 2. So on this problem, the factors of 1 are 1, the factors of 2 are 1 and 2. So our possible roots were plus or minus 1 over 1 and plus or minus 1 over 2, or plus or minus 1 and plus or minus 1/2. We would then go ahead and substitute into the polynomial function. The ones we should check are negative 1 and negative 1/2. When we substitute in, this is what we end up with. When I substituted in negative 1, I got negative 3. When I substituted in negative 1/2, I got negative 7/4. Neither of those worked out to 0, so that meant there were no rational roots on this particular problem. Now that doesn't mean there weren't real roots. There were 2 real roots, just no rational roots. At this point, do the following examples and then check your work. As you check your solutions on number 7, the first problem had 2 changes, so there were either 2 real positive roots and 0 imaginary, or 2 imaginary and 0 real positives. When you substituted in negative x, the only possibility is 1 real negative root. You can't do anything with imaginaries because there's not enough negative roots to take out a pair. On number 8, you get 1 real positive root, and when you substitute in the negative x, you get 2 or 0 real negative roots. Number 9 is a cone, and if you notice, the 15 is the radius of the sphere, so it goes from the center to the side and the center up. That means the height of the cone is actually 15 plus x. So when I wanted to find x, I took the height of the cone minus 15. I simply substituted in the values that I had for the formula, solved for h, solved for the height of the cone, and then subtracted 15 and ended up with x equals 0.36 centimeters. This concludes today's podcast.